My name is Mulalo Maphugwi. I'm a PhD candidate at the University of Cape Town. And today I'm going to talk about the climatology of mesoscale convective systems over Southern Africa. So what is a mesoscale convective systems? Mesoscale convective systems are classified as organized classes of convective storms that extend to several hundreds of kilometers and they persist for several hours. They are key for rainfall, distribution of heat, moisture, as well as energy throughout the atmosphere. But they also are associated with extreme late weather, such as damaging hail, lightning, as well as flash floods. So on the left of the screen there, you have a mesoscale convective system, a very massive system that was identified over Southern Africa in 2020, around the 23rd of December. So where are these systems usually found? These systems are common feature in the tropical as well as mid-latitude regions over the world. They form over oceans as well as over land. As you can see with the first figure there, you have a new number of MCS per year over the tropics. They usually are common feature. Over Africa, they usually occur over Central, West, as well as Southern Africa. Central and West Africa have recently received a lot of studies when it comes to these systems. And Southern Africa has seen a limited number of studies when it comes to these mesoscale convective systems. This is despite the identification of several hotspots. As you can see with the second figure there, there's a convective hotspot that you can see over Southern Africa. So why are these systems important? Over Southern Africa, it is projected by the IPCC that in the future there's going to be a decrease when it comes to average rainfall, but they are also projecting an increase when it comes to extreme rainfall. Mesoscale convective systems being a massive contributor in both average rainfall and extreme rainfall, it is very important for us to have a very good understanding of these systems over this region. So what I'm going to present and what I've always focused on over the past few months is to build a long-term data set of mesoscale convective systems over Southern Africa using one of the tracking algorithm called PyFlex Tracker. I've applied this in observation as well as high-resolution model. So on the left here, you have a snapshot of how this tracking algorithm tracks this mesoscale convective system. On a certain day, you can see the track path as well as systems that are identified, as well as the associated cloud risks. So we're going to focus on Africa, which is south of the 10 degrees south, which is Southern Africa. And then we are looking at two small domains, the one in blue, which we call the Congo Air Boundary region, as well as the one in cyan, which is the Mozambique Channel region. And then for observation, we use two high-resolution satellite datasets to analyze and track MCS over the region, which is the NASA brightness temperature, which comes at 4 kilometers, as well as the precipitation data from IMAGE, which is come at 10 kilometers. So the 4 kilometer brightness temperature is then regraded to 10 kilometers to match the precipitation data set. And then the tracking is done for 2000 to 2024. This is the time period that we have the data. And it is done hourly and also in austral summer month, that between October and March. There's a lot of tracking algorithms that have been developed over the past few years when it comes to tracking mesoscale convective systems. Here we are using one of the recently developed called Python Flexible Object Tracker, PyFlex Tracker, to identify and track this mesoscale convective system time evolution. So when you're identifying and when you are tracking these systems, usually you are tracking a very cold cloud shield that has brightness temperature as well as precipitation characteristics. So the challenge in doing so, given the climate of Southern Africa, is that you also tend to identify high and always precipitating systems that are cyanotypes, such as tropical cyclone, frontal systems, and also cold fronts, especially in the south. So we need to remove such systems in the database. So in order to remove tropical cyclones in the mesoscale convective system database, we used an IB-Track global database that has all tracked tropical cyclone. We created a 500 kilometer mast around each tracked tropical cyclone, and then any MCS or any tropical cyclone within that 500 kilometer mast is thus removed. This is shown by an example of a system or tropical cyclone called Filippo that occurred over Southern Africa, I think around last year. And then we actually created a mask and then a 500-kilometer mask around it. As you can see, it was actually identified and tracked as a mesoscale convective system. This is because of its brightness temperature, which is very, very cold, as well as its precipitation. This was then subsequently removed from our database. And then the second thing is that given the position on Earth of Southern Africa, you actually tend to get a lot of frontal systems or cold fronts, to be specific. And then this system also have high or a lot of precipitation that comes and that is associated with them. In order to remove them from our database, since they are also tracked, we introduced a feature called a shape complexity index, which measures the overall polygon shape and or complexity or irregularity of all tracked systems. This is because going back into the definition of a mesoscale convective system, we know it's very organized feature with a core, which is very, very strong. And then most of these frontal systems that gets to be tracked, they don't have these features of a mesoscale convective systems. They just have high precipitation. So we said that for a very, very irregular figure, that have a shape complexity which is closer to the 0, which is greater than 0.5 for more than 50% of its lifetime, actually get to flag this feature and then subsequently remove it from our tracking database. The two example over there, you are looking at two features with an SEI of 0.76 and SEI of 0.68, which is closer to 1, showing the irregularity. And then the bottom figure here, you are looking at a very nice, good-looking mesoscale convective system with an SEI of 0.25, which is closer to 0, showing how robust this methodology is when it comes to identification of these irregular features. After doing a few sensitivity testing in both brightness temperature as well as precipitation when it comes to PyFlex tracker, it's very technical, so I'm not going to go through the sensitivity testing that we did. We came with a mesoscale convective system framework on how to identify these systems over Southern Africa. So this framework goes in the fact that we identify a cloud system with brightness temperature threshold of minus 38 degrees Celsius or 235 Kelvin. It must have a core of minus 52 degrees Celsius and an area of 40,000 kilometers squared. It needs to have some sort of precipitation in a sense that it has 5 pixels with precipitation over 2 millimeters per hour. And then there is no heavy precipitation requirement for this system over the region. And then these criteria need to continuously be met for 4 hours or more. We introduced the system to remove tropical cyclone on number 5, and also the shape complexity index to remove frontal systems. After all that, we came up with the mesoscale convective system climatology over our region. So what you're looking here is MSC track origins in the first figure, as well as MSC track full path for the whole study period from 2000 to 2024 during austral summer months. And then you can see the hotspots of where this system usually occurs, which is the Congo Air Boundary region, which is over Madagascar over there, and also northern parts of Mozambique. You also have a secondary hotspot, which is over Southern Africa over there. And then going into mesoscale convective systems characteristics, here we use the two subdomains that we defined in the previous one, which is the Congo Air Boundary region, as well as the Mozambique Channel, to look at the time of initiation of the systems, the time that the system reached maximum extent, and then the time of termination of the systems, as well as the duration. So we found that this system usually occur between 11 and 4 p.m. local time. That's when they usually start to initiate. They reach maximum extent between 20 to 22 p.m. in the evening, and then they actually tend to terminate around just after midnight, showing their nocturnal nature. They usually last between 12 to 17 hours, most of them. And then over the Mozambique Channel, that's where you have some of the MSC based over the ocean that tend to last over 24 hours. And then here you're looking at the seasonal cycle of these systems during austral summer months from October to March, We found that the occurrence of mesoscale convective system is tied with the southern migration of the tropical rain belt, in a sense that during the early summer months, it starts to appear over the Cape, and then as the summer progresses, as well as the southern migration of those tropical rain belts, they tend to be to disperse over the whole region. Over the Cape, they tend to peak between December and Jan, but over the Mozambique Channel in the east, they tend to peak between January and February. And then when it comes to the rainfall that is associated with these mesoscale convective systems, you have about 2 to 3 millimeter rainfall per day, which is the rain rate in austral summer months in most parts where these mesoscale convective systems occur. This rainfall can reach about 4 millimeter per day in areas that is closer to the tropics. That's Madagascar over there, northern parts of Mozambique, as well as Angola, as well as some parts of Zambia. When it comes to the contribution of these systems to the rainfall in total during austral summer months, we found that the rainfall contribution can go up to 40 to 50% over the Cape region over there, and then Madagascar and Mozambique region and central parts of Mozambique, as I said, as well as Zambia. This contribution can be very, very high, which means that they are very, very important for rainfall over the region. Now we move over to these systems, mesoscale convective system as system models. General circulation model, as we know, have often failed to represent the system due to the mesoscale processes and interactions that happen between mesoscale convective systems and the model resolution failing to resolve those systems. But with the introduction and the recently seen high rise in convective permitting models, which have been shown to better represent convection, mesoscale convection systems can now be better represented. But unlike general circulation model, which are actually cheaper to run, you tend to have many simulations, but they cannot really resolve this model. When it comes to convecting permitting models, they are very, very expensive to run these models. So you tend to have one or two. So you cannot have that model spread that you usually have when it comes to general circulation model. Here we're going to look at mesoscale convective system in ICON, which is in the historic model of ERIE simulations. So they are tracked and then simulated in ICON, and then we will compare this with the observation for the similar time period of 2000 and 2014. We tried this with PyFlex tracker as we did with the observation, but the only difference is that we use the original setting of PyFlex tracker. These are the settings that are used in FANG 2021, in a sense that it has rainfall of 2 millimeter and a heavy rainfall of 10 millimeter when it comes to the thresholds. Obviously, the model doesn't have brightness temperature, so it has outgoing long wave radiation. So there is a convection that needs to be done in order to have brightness temperature. So this is the formula. I'm not also going to go deep into that to convert outgoing long wave radiation into brightness temperatures. To the next slide. So now you're looking at mesoscale convective system occurrence as well as frequency between ICON and observations. So you can see that ICON try to identify the MCS hotspots over the Cape region, the central parts of Angola, as well as northern parts of Mozambique and Madagascar, similar to how it is done in the observations. The only drawback with the model is that it overestimates MCS, especially in central parts of South Africa over here, as well as over the Cape region over there, where you actually have a lot of mesoscale convective system identified as compared to what you see in the observations. So the question is, why is the model seeing so many MCSs over the West? So due to the SST bias, I think Mr. Storman showed literally a similar figure in this the last one that we had. There is an SST bias, a positive SST bias from ICON that you see here in the Angola, on the Benguela current region. That's the coast of Angola as well as Namibia. There's the warm SST bias that you see that results in a lot of moisture being advected into the area. And then as a result, there is a high rainfall, as I showed earlier. Due to that, you actually tend to have more MCSs being picked in the west of Southern Africa. And then going down, thank you, Ramiro. So going deeper into the characteristics of these MCSs, here in the first plot, you're looking at the seasonal cycle. The blue one is the Cape region, and the red one is the Mozambique Channel. So it is interesting to see that in the east, there is generally an agreement between ICON as well as observation in the number of these systems, but over the west, where you have that bias, there's no agreement. That is the blue plots, where you've seen that the observation as well as the model doesn't really agree well. We also looked at the duration of the storms between the two domains. In the east, there's general agreement between model and observations, but when you go to the east, the model picks a lot of systems that are short-lived, between 12 to 14 hours. The observation picks a lot of short-lived systems, while the model picks a lot of long-lived systems, over 24 hours in the Cape region, in the west over there. And then we also looked at the density of mesoscale convective systems. That is the max area per grid point that we created using the polygon of each cloud shield of a tracked MCS at its maximum extent, and then summing them over and then dividing by the number of seasons. You can see that with the model, with ICON, there is 3 peaks, which is in the central Angola, northern Namibia, northern Mozambique, as well as Madagascar. But on the observation, most of the MCS tend to just reach the maximum extent just over Madagascar. So just to conclude, there's the next steps that we're going to be looking at. We need to do some more sensitivity on the model simulations. For example, the SERI that we introduced in the observation, how will it hold in the model? And then also in the past few weeks, we have gotten more model simulation. Thanks to Chatro and Pablo, we have IFS NEMO historic, OLR hourly, as well as precipitation. We are also going to use the IFS vessel from NextGems that has the variables that we need. We also, so the simulation with ICON that I showed, especially over the east, tend to have some tropical cyclones that are tracked as mesoscale convective systems. That's because in the models, we don't have IB tracks. So we need to find a way to remove the cyclones in the database, especially when it comes to models. So we need to actually run another tracking algorithm to track those cyclones. But if there is somebody that is doing that with the EERIE simulation, especially ICON, then we can get in touch so that we can see how we can work. And then also we need to look at the contribution to rainfall when it comes to the models. So we're going to do this for all the models that we're going to run, not just ICON for now. We'll do that with IFS NEMO as well as FASOM when we do this tracking on those models. And then we also need to look at the projections and change when it comes to mesoscale convective systems. How are they getting a stream, especially in the future projection of rainfall as well as over Southern Africa. And then with that, I conclude. Thank you so much.
So we are going to the second speaker, which is Rohit Ghosh. He will be talking about climate variability and change in EERIE simulations. So Rohit, again, 15 minutes. I will let you know, and the floor is yours.
Thank you for this opportunity today. So today I am going to present some preliminary results. So basically, we are going to talk about climate variability and change, but my focus of today's talk is on temperature. One second. Temperature variability over the tropical Pacific, which kind of controls the climate variability quite a bit of our planet. So first, I would also like to thank all the EERIE modeling teams who are providing the data and simulating the models so that we can do this work. So first, let's go to the motivation of the science here. Is the observed sea surface temperature trend. So this observed sea surface temperature that we can see here in the left is from Watanabe et al. Is from the ERSST trend. And you can see that until 1979 to 2013, the trend shows this cooling in the eastern tropical Pacific and the warming in the Western Tropical Pacific. This is very important to understand these changes in the Pacific temperature, because it drives the global circulation, changes the weather, and it will have an influence on the weather and the climate, regional weather and climate. And then in the bottom, you see the same temperature trend, but until 2022. So basically what we see in observation is the western part of the Pacific Ocean is warming, the tropical Pacific, and the eastern part is cooling. So the gradient of the zonal SST gradient is getting stronger. And that bringing a stronger Walker circulation, and also it has an effect, a pattern effect of the SST pattern has an effect on the radiative feedbacks that we get, and also the energy balance. But what is the issue is that in the low resolution CMIP model, CMIP 5 or CMIP 6, or in even in large ensemble simulations, we don't find this evolution of the tropical Pacific. So it appears very not so often, seldom in a few simulations in the large ensemble. We sometimes see this pattern, which makes made mainly during the period of 1979 to 2013. After that, all those studies that came that tried to see this pattern, and then found this pattern in few ensemble members, which led to believe that it would be due to internal variability, especially the interdecadal Pacific oscillation, which shows this kind of pattern. But afterwards, when the record further came, we could see the trend from 1979 to 2022. The trend, it's not getting so similar to the typical IPO pattern, and then this cooling pattern in the Southern Ocean to the eastern side of the tropical Pacific still lingers, still exists. So still, that's why it's still scientists are thinking that it's maybe there is something more than the internal variability that's behind this signal that we are seeing. So there are also different kind of explanations of why this could happen. So there are some from the energetics framework, some from the dynamical frameworks. Different kind of mechanisms are proposed that could lead to this kind of pattern. And one of those is energetic framework is the interhemispheric temperature gradient. So if your one hemisphere is warm and one hemisphere is cool, so if there is, suppose the Southern Ocean cooling, then it adjusts circulation, and the ITCZ moves accordingly, and then it brings certain circulation features that could bring the cool temperature in the eastern part of the tropical Pacific. So I'm going to be mainly dealing with this mechanism and seeing this mechanism. So now our question is, the open question is, can high resolution coupled model could show something different than what we are seeing in previous generations of models? So here is the same SST trend in all in the 4 EERIE simulations. 3 of them, IFS FESOM, ICON, and IFS NEMO, had this simulation starting from 1950. All are below 10 kilometer resolution atmosphere, and the ocean also in high resolution below 10 kilometer, and also had GEM3 high resolution, which is also almost 10 kilometer, like close to sub 10 kilometer resolution, but a little bit above. But they are the highest resolution simulations in the EERIE project. Historical simulation trend from 1979 to 2014 compared to the observations. And you can see one feature is all of them having a little bit of this Southern Ocean cooling. And then the model which has the strongest Southern Ocean cooling has the strongest Eastern Equatorial Pacific temperature, cool temperature that we see in the observations. So the most strongest here is ICON, and ICON is also, I think, working on it further so that they found this strong response. We will come back to it, maybe why it's so strong there compared to the others. But also in IFS NEMO simulations, we see Eastern Equatorial Pacific cooling trend appearing, and also IFS FESOM, it's much milder, but it still exists there. And also HADGEM kind of showing a gradient in the temperature. You can see Equatorial Pacific is warm in the western part, and the eastern part is comparatively cooler, the temperature trend. So first of all, this is a feature, the HADGEM simulations is a little bit different protocol. It did a long control run, and then it moved to the historical simulations. So that already performed a long control simulations, but for the other 3 models, we have a shorter control simulation. So that's why we have a parallel control spin-off simulation. So that's why we have a parallel control simulation going with this to understand if there is a contribution of the drift in it. So it would be better before going further, we make sure that the drift is not bringing this cooling trend. So here you can see drift adjusted SST trends. So first is icon. So left is the historical trend, the historical simulation that you have seen in the last slide. And then I'm showing for the same period, the trend in the control. So it's showing kind of the model drift pattern that could have been contributed to the trend if we assume linearity, and then a difference of that. So basically for icon, it even flares up the signal further. And if we see for IFS NEMO, we still have the cooling trend patterns when we look at the difference in the right side when we adjust for the drift. So the drift has an overall cooling tendency over the globe, but when we subtract it from the historical sense, we still find it. And IFS FISM also, the Southern Ocean cooling signatures, very faint, but it still persists, and also there's a little bit of cooling pattern coming. There could be also internal variability strongly involved here because IFS FISM has very strong ENSO variability, which has a lot of positive phase ENSOs at the end of this period. So that could be bringing more warming in the end. But we can go back to it later in a little bit. Further, what I wanted to check is now what happens to this trend if we extend this trend plot until 2050, the total scenario simulations, because we have a small period, more noise coming into the signal in a small sample, and we might see signal noise mixed up. But then when we go until 2050, we still, for IFS FISM, it's kind of getting better. So we have a little bit of the cooling pattern still exists in the Southern Ocean, and the branch over the Equatorial Pacific is still not as clear compared to the other models. There could be other reasons for it, but we can see a little bit of signature of that opposite side C pattern that we see, horseshoe pattern that we are expecting here. For icon, the pattern is still existing. So until the mid-century, we're still finding this trend pattern kind of exists in the icon, which has shown the strongest signal. And IFS NEMO also still showing the signal of the Equatorial Pacific and HADGEM. So they're in varying degrees showing some signs of capturing this mechanism of the Southern Ocean cooling relating to the Eastern Tropical Pacific connections. Also, apart from that, there is also varied warming hole, North Atlantic warming hole, which is not the topic today, so I would not delve into it. But you can overall, what you see there regarding North Atlantic warming hole, the model that has shown the weakest AMOC kind of having the strongest warming hole by the end of 2050, which is IFS NEMO, and then in varying degrees of the AMOC, it's quite connected, it looks like. So next is what is the role of resolution? For that, we have the HADGEM model, which has done simulation in 3 resolutions. So low resolution kind of CMIP like MM kind of close to high-res MIP 1 resolution around 30 kilometer, and HH the highest resolution that you have seen before. So that we can take a help of. I still have to do it for including the scenario period, but here you can see there is some role of resolution for the same period of time, at least. Although we see a Southern Ocean cooling in the LL model, we don't see that signal coming further and creating a signal in the tropical regions of the Pacific, in the southern tropical regions. But as we are moving to the higher resolution, especially in the MM model, we can see a very strong Southern Ocean cooling. I am not sure why, but then regarding that, we also see this pattern popping up a little bit more prominently, and also in HH, the position of the pattern is actually a little bit better in the HH, which is coming more towards the equatorial region that we expect, also very mild. So next is Pacific temperature variability. So the main variability that's governing our global climate variability is ENSO. And maybe I will try to give indication or hint that I could think that could be the reason why this signal is so strong that we've seen in the trend in icon compared to the other models. Why icon is so strong, or even also showing a little bit unrealistically going too far to the west, the signal of the cooling. So here is the ENSO patterns of the different models. So had ISST, so it's from 1950 to 2014, the historical simulations ENSO patterns in all the models, and you can see they're all capturing except icon. There is some difficulties in icon as we go, and maybe we already know a little bit about that icon has difficulty capturing ENSO, but in the other models, the patterns looks quite nice. Actually, for HADGEM also, this westward extension of the ENSO branch, which is a typical CMIP model problem, that is coming a little bit better. It's less westward extended ENSO branch that we can see, but the global pattern are varying in different models. Suppose for HADGEM, the associated pattern in North Atlantic is all positive anomaly mostly. So, and then some the pattern in the Indian Ocean is better, some less. But now when we make an ENSO spectrum, so we can see we are expecting the main ENSO variability during the highest energy spectrum during 2 to 7 years band, and you can see in all the models, the black is the observation, HAD-ISST, green, IFS NEMO, blue, IFS FISOM, and ICON. You can clearly see the ICON has no variability in ENSO. So the ICON power spectrum kind of drops, showing a very less variability compared to what we expect from the models. So maybe the idea here is that because variability is the noise, so ENSO variability, the internal variability, as the noise is so less in icon, we see the signal, which is the trend with the forcing, this cooling pattern could be the signal, which is so strong because the underlying, the variability that's coming from ENSO is really diffused in that model. But it might be having some other impact, so we actually don't know that if it is a real signal. So when the ENSO would have been in its proper dynamical phenomenon, if that signal would evolve that strongly, that is also not clear. So persistence and phase lock, so we do persistence, which shows that the ENSO drops, and then in a later phase, ENSO has this 40 to 60 months, which is 3 to 4 years, ENSO again pops up. So you can see as the icon has no variability that much, it's kind of persists in the short time scale. There is no strong variability for the persistent autocorrelation of the NINO 3.4 index to go down, so it kind of stays there and then goes up. And then another thing is the phase lock, which is actually the monthly standard deviation of the ENSO index, which shows that in the winter the ENSO is the most strong, the ENSO variability. So in all the model simulations, you can see that the ENSO is stronger in variability compared to the observations, which is this is the black line, and most closest capturing the phase lock is HADGEM, which is kind of dropping in the spring, April or May period the most, which is having an issue in IFS FISOM and IFS NEMO, which drops to the minimum during the midsummer. So at least the phase lock feature is most better captured in HADGEM, but you can see in icon it's just fall flat out. There is no phase lock, so there is no higher variability in winter, lower variability in summer. So the whole ENSO dynamics is kind of a little bit out of focus here. But mainly the point is variability is very diffuse. So maybe the forced cooling pattern emerged so strongly because there is underlying variability. The noise is almost not present or very diffused. So on that note, I want to conclude now that the EERIE models tend to reproduce, we can say, observed Eastern Equatorial Pacific cooling trend, which is, I would tend to, because we need some more ensembles to really confirm it in some way, but there we see some sign of it with especially the Southern Ocean cooling. That was also an issue in the model, but we are kind of seeing all of the models are getting some level of Southern Ocean cooling in varying intensity, and then the Pacific response persists to mid-century. So we see this response is still there, although studies previously were suggesting that it will change at some point, but we reached almost 2.5 Kelvin warming by 2050, and we still see the signal there. With all models, a relatively warmer Western Pacific, and resolution plays a role. Of course, HADGEM3 we saw LL low resolution was not getting, but as we go to the high resolution, there is some role of resolution. Although Southern Ocean, getting the Southern Ocean cooling is quite important, and then connecting it to the Eastern Equatorial Pacific. ICON is an outlier with usually strong response, and raising a question why we got so strong. So if we look into the ENSO and then from the variability, we see that the ENSO variability is very weak or diffused in the ICON, and then maybe that's causing the post response if we consider the cooling and the associated response coming so strongly, because the signal to noise ratio will be high. So basically the planned future work on this regard, the work that would be to look in this zonal SST gradient and see what all these models are, how they evolved and associated circulations. And then precipitation response or global circulation response, how they are looking compared to what we see in observations. And also the main part is the Southern Ocean. The next talk is on Southern Ocean sea ice, so maybe we see some aspect there, but Southern Ocean SST and sea ice, how it's evolving with regards to that. And then we look forward to get the ensemble simulations. So as we are seeing some signs of the signals on, maybe it will help us to understand if we are getting that consistently, or the noise to reduction of noise, because we don't have all the diffused and so to have the signal so strongly there. So on that note, I would like to thank you all for your time.
Thanks, Rohit. Thank you very much. So we're going to the third speaker. We are not moving very far from Rohit's area of research. We are staying basically at the Southern Ocean. So it's Cécile Davrinche, who will be talking about sea ice and heat fluxes in the Southern Ocean.
All right. Thanks for having me. So good afternoon. I'm going to talk about the sea ice and a bit about the heat fluxes in the Southern Ocean in the EERIE models. I just wanted to give a bit of context about the sea ice, especially in the Southern Ocean. So there is a big difference between the sea ice in the Northern and in the Southern Hemisphere. In the Arctic, there has been a constant decline since the 80s in the sea ice area, while in the Antarctic, there was an expanding phase from 1979 to approximately 2015. And one of the big question in the field is to understand why we did have this expansion phase in the Antarctic sea ice while the rest of the world was warming. This is something that is really important since models usually fail at simulating this expanding phase. So many different reasons have been brought to explain why models failed to represent the increasing phase of the sea ice area until 2015. Some people say that it's because of the biases in sea ice drift velocity. Some say that it's about wind changes or random variability of the climate system. And recently, in 2022, some people stated that it was because of the eddies. So the solution was to have eddy resolving models, and in eddy resolving models, we could have a more realistic representation of the Southern Ocean, and thus this increasing phase of the sea ice area in Antarctic. So the first question that arises is, do EERIE models caption this increasing phase of the sea ice area in the Southern Ocean? And do EERIE models perform better than SEMIP6 models at representing the mean state of the sea ice? So I think you've already all seen these maps of the sea ice in the EERIE models. The red line represents the OCSAF observations, and that's the state of the mean state of the sea ice for September 1979 to 2014. So as you can see, there are some large biases in all EERIE models. These biases have been well documented by Nadine's master thesis. So it includes an early sea ice decline, underestimation of sea ice, and an intensified Antarctic slope current. So we see that we have a lot of biases in the sea ice for the EERIE models, but that doesn't mean that it's worse than the previous models. So let's compare that to SEMIP6 models. Well, here, if we compare the mean September sea ice area and the mean February sea ice area between the SEMIP6 models in blue and the EERIE models in brown to the observations, which is the black dot, we see that we do not improve the representation of the sea ice area from SEMIP6 to EERIE models. It's also the case for the mean sea ice area in February. If we look at the standard deviation, it's actually worse in EERIE models than in the mean SEMIP6. And if we take a matrix of the error between the sea ice area in EERIE models and in the observations, it's actually also worse in EERIE models than in SEMIP6. And something that I think haven't been said before is that This is partially due to the fact that all EERIE models actually exhibit some polynya, open water polynya. So I've highlighted the open water polynya in green on the left. And you see that for PESM, ICON, HADGEM, but also I've included another high-resolution model, which is a CESM1HR. I've included this model because it has 10 members, so it's always good to have a look at the different members for the internal variability. So we see that all high-resolution models have some polynya during wintertime. And that's one of the reasons why we do have large biases in the sea ice extent. So if I had to answer to the question, do EERIE models perform better than CMIP6 models at representing the mean state of the sea ice? I would say no. For the mean state, they are actually performing a bit worse than the CMIP6 models. But the fact that it's not correctly simulating the mean state does not mean that we cannot have any information from it. So the second question is, we know that we do not simulate well the mean state of the sea ice, but is there a chance that we can maybe understand the increasing phase, the expanding phase of the sea ice using the EERIE simulations? Once again, some papers had stated that if we had eddies in the model, if we were resolving eddies in the models, we would have better heat fluxes, and thus we could simulate this expanding phase of the sea ice. So we don't have this increasing phase of the sea ice in all the EERIE models, but if we separate it by sectors, we do have some regions where there is an expanding phase of the sea ice in Antarctica. For example, here I've separated, it's for ICON, I've separated it into 3 sectors, depending on longitude. And we see that for sector 1 and sector 2, there is an increasing phase, an expansion phase of the sea ice for both sectors, which is not something that is observed in sector 3, but sector 3 is also the sector where we do have polynyas. So the question is then, in these sectors where there is an increasing phase of the sea ice, can we actually maybe get some information or understand what's happening? So when I first started working about it, the hypothesis that we have was that it would be a two-step mechanism. First, heat would be stored in the ocean, maybe because of stratification in the deep ocean, and then heat would be released to the surface, and that would trigger a sudden decrease of the sea ice extent. So the behavior from the sea ice that I was expecting was that there would be an increasing phase. During this increasing phase, the oceanic heat content in the first hundreds of meters of the ocean would decrease, while it was increasing, was increasing in the first 100 meters, decreasing in the first 100 of meters, while it would be increasing in the bottom part of the ocean where the heat would be stored. And then once the stratification would start to decrease, the oceanic heat content would start to increase in the first 100 of meters, leading to a decrease of the sea ice area. So that was the behavior I was expecting when I first started looking at it. And if we actually look at the oceanic heat content at different depths for ICON, we don't necessarily observe this expected behavior. For example, if we have a look at sector number 1, we don't really see any difference in the oceanic heat content stored in the few hundred meters of the ocean between the increasing and the decreasing phase. And it's also the case in the sector number 2. However, for the oceanic heat content stored in the lowest layer of the ocean, we do see some differences between the increasing phase. For example, during the increasing phase, there is more heat stored in the bottom ocean for sector number 2, and then a sudden decrease after. But it doesn't necessarily, so the timing does not really match with with the decrease in the sea ice area. So this is some work in progress, and if you have any thoughts about it, I would really appreciate some insight. About it. So these are my conclusions. There are larger biases in EERIE models and semi-physics models when it comes to the mean state of the sea ice area, and absolutely all high-resolution models simulate unrealistic polynya, especially FESM. So it leads us to the conclusion that high resolution only does not enable for a better representation of the sea ice. And last but not least, if anybody has some opinions or ideas about the partition of the oceanic heat content in the ocean, I would be really happy to hear them. Thank you.
So thanks to the three speakers for your very interesting presentations. Before closing the meeting, just a short advertisement. Next month, we have the last Science Hour of the year. It will be on December the 15th at 2 p.m. as usual. It will be hosted by Katia Weigel, and the participants or the speakers will be Jan Hendrik Miles from the University of Bremen and Bobby Antonio from the University of Oxford. They will be both talking about Jan, causal model evaluation of Southern Ocean air-sea interactions. And in the case of Bobby, he will be dealing with artificial intelligence and preliminary results on coupling a machine-learned atmospheric model, ACE2, to a dynamical ocean and seasonal forecasting with GenCast. So it seems to be a couple of very exciting talks. So see you next month. And thanks again for your time and the three speakers for your very interesting presentations. So see you soon.